Chapter 4. Three major classes of chemical reactions. These are the topics we are going to study. Solution concentration and the role of water as a solvent. Writing equations for aqueous ionic reactions. Precipitation reactions. Acid-base reactions. Oxidation-reduction reactions. Elements in redox reactions. The reversibility of reactions and the equilibrium state. In a solution, the substance with a smaller quantity is called solute, and the one with larger quantity is called solvent. In an aqueous solution, water serves as a solvent. Some solvents passively disperse the substances into individual molecules, but water is much more active, interacting strongly with the substances and even reacting with them in some cases. These diagrams show electric distribution in molecules of hydrogen and water. In A, we use a space filling model to show electric charge distribution of a hydrogen molecule. There are two nucleus of two hydrogen atoms surrounded by electron clouds. The red color indicates high electron density. The blue color indicates low electron density. There's a high electron density between the two nucleus, indicating a covalent bonds. Now, because the two hydrogen atoms are identical, the electron charge distribution in this molecule is symmetrical. In B, we also use the space filling model to show electron charge distribution in water molecule. There are three atoms, oxygen and two hydrogen atoms. Again, the red color indicates high electron density and the blue indicates low electron density. And now you can see there are high electron density around the oxygen than on the hydrogen. So oxygen attracts electron more than hydrogen. And these bonds, oxygen-hydrogen bonds, even though it's a covalent bonds, they share electron, but the electron is attracted more to oxygen. It's not equally shared. This kind of bond is called a polar bond. So the bond is polar. So the oxygen has more electron density than hydrogen atom. Now this is more clearly seen in C. Use ball stick model. You can see two hydrogen oxygen bonds. Both are polar, and this arrow indicates the electron clouds goes to oxygen, and the hydrogen has a positive charge. Positive means electron deficient. Negative means high electron density. So there are two polar bonds in this molecule. Now, if these two bonds are in the same line, then this molecule, two polar bonds will cancel each other, and that is similar to the case where you pour a strain to 100 degrees to the left and the right. The center will not move because the two forces cancel each other. If you pour left and right with the same force, then the center will not move. If, however, you pour at a certain angle, instead of 100 degrees, you pour at a certain angle, then the two forces cannot cancel each other, and the center will move down towards the downwards. This is the case in water molecule. There are two polar bonds, but they have a certain angle, and therefore the net effect is that the molecule has more electron density around the oxygen, has electron deficient on hydrogen side. So oxygen is negative charged, and hydrogen has positively charged. And this has an important consequence as a solvent for water molecule. In an ionic compound such as sodium chloride, positive charged sodium ion is surrounded by negative charged chloride ion. and the negative charged chloride ion is surrounded by positive charged sodium ion, as shown in this diagram. These ions are attracted to each other by electrostatic force. What happens if a piece of sodium chloride solid is placed in water? As we already know, water is a polar molecule. Oxygen has more electron density than hydrogen, so oxygen is partially negative charged, and hydrogen is partially positive charged. The partially negative charged oxygen attracts positive charged sodium ion, as shown here. And the positive charged hydrogen attracts negative charged chloride ion, as shown here. When this attraction force between water molecules and the sodium ion, so sodium ion and the chloride ion, when these attraction force outweigh the attraction force between sodium ion and chloride ion, these ions start to leave the solid and go to the solution, become dissolved. Each chloride ion here is surrounded by water molecules, and each sodium ion is surrounded also by water molecules, and this prevents these ions to go back to the solid. Although water molecules are polar, so oxygen is partially negative and hydrogens are partially positive, the whole molecule is neutral. So in pure water, there's no significant amount of charged ions, even though water auto-ionizes to form proton and hydroxide, but the concentration is 10 to the minus 7, so pure water has no significant ions that conduct electricity. So pure water do not conduct electricity. Now, ionic solid, such as sodium chloride, does not conduct electricity either, because the positive and the negative ions has a fixed location that cannot move freely, so they cannot conduct electricity. When ionic compounds dissolve in water, okay, so for example, sodium chloride, now you have a negative charged chloride, positive charged sodium in the solution that can move freely, conduct electricity. Note that negative charge, positive charge move to different opposite direction to conduct electricity. A substance that conducts a current when dissolved in water is called electrolyte. A soluble ionic compound is a strong electrolyte because it dissolves in water and dissociates completely, becomes negative charge and a positive charge that conduct a large current. So what are the ionic compounds that are soluble? Well, there's a solubility rule we're going to explain later, but basically group 1 cations, potassium, sodium, lithium, okay, all group 1 plus ammonia. So salts containing these cations are highly soluble. For example, sodium chloride, potassium bromide. Okay, so ionic compounds containing group 1 ammonium ions, these are highly soluble. Okay, salts containing anions such as nitrate, perchlorate, okay, are also highly soluble. For example, copper nitrate. Okay, it's a soluble. Okay, any salts containing anion nitrate and perchlorate. Okay, we'll explain more later in this chapter. Sample problem 4.1. The beakers shown below contain aqueous solution of the strong electrolyte potassium sulfate. Question A. Which beaker best represents the compound in the solution? Water molecules are not shown. To answer A, we first need to determine the formula and write an equation for the dissociation of one mole of the compound, potassium sulfate. Potassium sulfate contains group 1 cation potassium, which is a strong electrolyte, and therefore it should dissociate completely. Okay, this is important because it's strong electrolyte. And also remember, sulfate is a polyatomic ion which remain intact in solution. So here is the formula, potassium sulfate. Okay, it dissociates into 2 cation, 1 anion. So we should look at electrolyte that completely dissociate and the ratio of cation to anion should be 2:1 ratio. Okay, so let's look at A. In A, anion cation is not completely dissociated, so this is not a strong electrolyte. Similarly, in B, cation anion are still associated, so not a strong electrolyte. C, anion cation are completely dissociated. So how many cations? So cations, we have 1, 2, 3, 4, 5, 6. Anion, we have 1, 2, 3. And the ratio is 2:1, and that's correct. So C is the correct answer. Now let's look at D. So in D also cation anion dissociated. But if you count cation, we have 3, but the anion we have 6. So the ratio is not consistent with the equation that the cation should be twice of the anion, and therefore D is not right. In question B, if each particle represents 0.1 mole, what is the total number of particles? Note that it's particles, not moles. Okay, so you need to times Avogadro's number to get the particles. And since the C, beaker C is the correct one, so we should look at the beaker C, count the number of separated particles, multiply by 0.1, because that's each particle represents 0.1 mole. So we get number of moles, and then we multiply by Avogadro's number, and that gives you how many ions in the solution. Okay, so if you count, you will see we have 6 cations, 6 potassium, and 3 anions. So the total is 9 particles in the solution. So 9 ions in the solution. 9 times 0.1, that give you number of moles, and then times Avogadro's number, and give you the particles. Sample problem 4.2. What amount moles of each ion is in each solution? A. 5.0 mole of ammonium sulfate dissolved in water. To answer this question, we need to write an equation for the dissociation of 1 mole of ammonium sulfate, and then use this information to calculate the actual number of moles of the ions generated by 5 moles of ammonium sulfate. Here is the formula of ammonium sulfate. One formula of ammonium sulfate generates 2 molecules of ammonium, 1 sulfate anion, or we can say 1 mole of ammonium sulfate. So here is 1 mole. So will dissociate, give you 2 moles of ammonium cation and 1 mole of sulfate anion. So if we have 5 moles of ammonium salt, okay, how many cation anion can we generate? So we look at each relation, the stoichiometry, write a conversion factor. So we start with 5 moles ammonium sulfate, and we write the conversion factor: 1 mole ammonium sulfate, 2 moles ammonium cation. So cancel the moles of the salt, ammonium sulfate, give you moles of ammonium cation, which is 10. To calculate the anion, we look at the relation here is 1-to-1 ratio. So we can also write a conversion factor: 1 mole ammonium sulfate, 1 mole sulfate anion. So again, the salt cancel each other, give you more of sulfate anion. In this case, it's also 5 moles. In question B, 78.5 grams of cesium bromide dissolved in water. So here is the formula of cesium bromide, which dissociate into 1 cesium, 1 bromide. Okay, note that this is grams, given is grams. Now the stoichiometry is in terms of moles. So first you need to calculate moles, convert grams to moles. So here is 78.5 grams, use molar mass as a conversion factor. 1 mole cesium bromide, 212.8 grams of cesium bromide. So you cancel grams, you get moles. Okay, so you get moles of cesium bromide, and then you look at the stoichiometry: 1 mole of cesium bromide, 1 mole of cesium cation. So moles cesium bromide, moles cesium bromide cancel, you get moles of cesium. So the answer is 0.369 moles of cesium cation. Similarly, you can calculate the bromide number of moles. Again, you should convert grams of cesium bromide to moles and use stoichiometry, and you can calculate. Now in this case, the ratio is 1-to-1. So whenever you generate 1 cesium cation, you also generate 1 bromide anion. So the answer is the same, 0.369 mole. In question C, it gives you 7.42 times 10 to the 22 formula units of copper nitrate and asks you how many moles of each ions. So we are given the number of entities. We want to calculate moles. First, let's write the formula, which is copper nitrate. Each copper nitrate give you 1 copper ion, 2 nitrate ions. Now, because given is number of entities, we first need to convert to moles and then use stoichiometry as we did in B to calculate the moles of each ions. Okay, so first we start with 7.242 times 10 to the 24 formula units and use Avogadro's number as a conversion factor. So the formula units cancel each other, give you 0.123 moles of copper nitrate. And then we look at the stoichiometry, okay, and 1-to-1 ratio. So we start with 0.123 moles of copper nitrate and use stoichiometry as a conversion factor. 1 mole of copper nitrate, so cancel copper nitrate, give you 1 mole of copper ion. And so the answer is 0.123 moles of copper 2+ ions. Similarly, we can calculate moles of nitrate. Now, because the ratio is 1-to-2, okay, here you have 2. So whenever we generate 1 mole of copper ion, you should get 2 moles of nitrate. And therefore, the answer should be double of this number, should be 0.246 moles of nitrate anion. Many reactions occur in solution. A solution consists of 1 or more solutes dissolved in a solvent. The concentration of a solution is given by the quantity of the solute present in a given quantity of the solution. One of the most common concentration is molarity, okay, M, which is calculated by moles of the solute divided by volume of the solution, and the volume is in liter. So moles solute, liter solution. Since molarity is the ratio of moles of solute and the volume of the solution, this can be used as a conversion factor to convert between the volume of the solution and the number of moles of the solute. Sample problem 4.3. What is the molarity of an aqueous solution that contains 53.7 grams of glycine in 495 milliliter? So first, what is molarity? It's the moles of the solute per liter of the solution. Do we have moles of solute? No, we have grams. So first we need to convert from grams to moles. Use molar mass. Okay, so use molar mass as a conversion factor. Molar mass can be calculated by looking at the molecular formula to calculate to be 75.07 grams of glycine. So grams of glycine cancel, give you moles of glycine. Okay, next we need to divide by volume, but in liter. So here is in milliliter. One way to do it is we first convert milliliter to liter, and then we use moles divided by the liter. Alternatively, we can combine these two steps into one. So we use moles divided by milliliter, and then convert milliliter to liter. 1 liter, 1000 milliliter. So use this as a conversion factor. We get moles per liter, and that's molarity. So 1.44 molarity glycine. Here shows the relationships in solution between mass, moles, number of entities, and the volume. And you can see the center is number of moles. Okay, suppose we know grams, we can convert to moles using molar mass. And with moles, we can calculate the volume of the solution, use the molarity we just introduced. And we can calculate the number of entities, the ions, for example, using Avogadro's number. Sample problem 4.4. How many grams of solute are in 1.75 liter of 0.46 molarity sodium hydrogen phosphate buffer solution? Okay, so we have volume, we have molarity, we want to calculate grams of the solute. Now let's look at the molarity. The definition of molarity is moles of solute per liter of the solution. So this can be used as a conversion factor. If we know the volume, okay, here we know the volume, using this as a conversion factor, we can convert into number of moles from volume, liter, to moles of the solute. And then from moles, we can calculate the grams. So moles, okay, of the solute, calculate grams of the solute by molar mass. So let's start with volume, 1.75 liter, okay, and then the molarity, 0.46 molarity means 0.46 moles of the solute per liter of the solution. Okay, so by using this as a conversion factor, we cancel liter, we calculate moles. Okay, so that gives you 0.805 moles of the salt. Next, using molar mass. So moles of the salt, okay, 1 mole sodium hydrogen phosphate, 141.96 gram of this salt. So moles cancel, give you grams. Sample problem 4.5. What amount of each ion is in 35 milliliter of 0.84 molarity zinc chloride? So again, we given is molarity and the volume. Now this time we want to calculate the moles of each ions. So again, we look at the definition of molarity, which is moles solute per liter of solution. If we have volume, we can use this as a conversion factor to calculate moles of the solute. And from moles of the solute, which is zinc chloride, then we can calculate moles of zinc ion and the chloride ion. But we need to know the formula and the dissociation reaction first. So here is the formula, zinc chloride, which dissociate to give 1 zinc 2+ and 2 chloride anion. And now let's use the molarity as a conversion factor to calculate the moles of the solute. Okay, so we note that the given volume is milliliter. So in definition of molarity is in liter. So you need to convert milliliter to liter first. Okay, so 35 milliliter. Okay, divided by 1,000 milliliter. So 1 liter equals 1,000 milliliter. So cancel milliliter, give you liter. All right, and then use molarity as a conversion factor. Again, what does molarity mean? Is the number of moles, in this case 0.84 moles of the solute per liter of the solution. So in this case, the liter cancel each other, give you moles of the solute. Moles solute is the zinc chloride. So you have 2.9 times 10 to the minus 12 or minus 2 moles of zinc chloride. Okay, now let's look at the stoichiometry. 1 mole of zinc chloride, 1 mole of zinc ion. So we can use the stoichiometry as a conversion factor. So you start with moles of the zinc chloride. Now if you want to calculate the chloride, then 1 mole of zinc chloride, 2 moles of chloride. So you see the stoichiometry is 1 to 2. So 1 mole zinc chloride cancel each other, give you moles of chloride. For zinc, you do the same step, but it should be 1 mole. So the conversion factor should be 1 mole of zinc, and that gives you 2.9 times 10 to the minus 2 moles zinc ion in the solution. Now, in the last step, we should check if the calculation is correct. And basically, you just look at the ions. So you have zinc 0.029 and the chloride 0.058. So the ratio is 1 to 2, which is consistent with the formula zinc chloride. This diagram shows how to prepare molar solution in laboratory. So, for example, if you want to make 0.2 molarity, 500 milliliter solution. So we use a volumetric flask, and which has a marker here to indicate that's 500 milliliter. And first step, you need to calculate how many grams of solute you need to make to 0.2 molarity. And then you weigh it accurately, the amount you needed of the solid. Transfer the solid into the flask with small amount of water first. Okay, you shake the flask until the solid all dissolve into the water solution. Okay, and then you add more water until solution touch this ring. So at this point, you have correct amount of the solute and correct volume of the solution. Sometimes we want to convert a concentrated solution to a dilute solution. For example, suppose we have a solution concentration 0.2 molarity, but in a particular experiment, we only need 0.1 molarity. So how can we do that? Well, we can measure the concentrated solution a certain volume, for example, 10 milliliter, okay, of this concentrated solution. And then we add equal amount of water, so 10 milliliter of distilled water. So the total volume double, okay? But the solute doesn't change, and therefore the concentration becomes half, from 0.2 becomes 0.1, okay? In a dilute solution, okay, if the volume are the same compared with the concentrated solution, the solute molecules has fewer molecules than the concentrated solution, okay, because you have more water molecules in it, and therefore you have less solute molecules in the dilute solution. Sample problem 4.6. Isotonic saline is a 0.15 molarity aqueous solution of sodium chloride. How would you prepare 0.8 liter of isotonic saline from a 6 molarity stock solution? So this question gives you a concentrated solution molarity, 6 molarity. And we want to dilute to 0.15 molarity, volume 0.8 liter. Now to dilute a solution, we need to add water, okay? But what is the volume of this stock solution do we need to make this dilute solution? So you add water until the total volume is 0.8, okay? But how much stock solution do we need, okay? To calculate this type of question, the key is to realize that no matter how much water you add, the solute moles does not change. Okay, when you add water, it doesn't change the moles of the solute. So you must remember this equation. Okay, the number of moles of the solute before and after dilution is the same. The number of moles of the solute is calculated by the volume times molarity. Okay, this is after dilution. This is before dilution, the concentrated solution. Okay, before, after, they have the same number of moles. So in this case, after dilution, the concentration and volume are both given, and therefore we can calculate the moles, number of moles of the solute after dilution, which equals the number of moles before dilution, the concentrated moles. So with this number of moles, and also we have molarity, then we can calculate the volume. What is the volume we need for this dilution? Okay, so let's first calculate the number of moles of the solute using the after dilution, the molarity and the volume. So we use volume 0.8 liter, and the molarity we write as a conversion factor 0.15 moles per liter of the solution. So per liter cancel each other, give you moles of sodium chloride. So this gives you 0.12 moles of sodium chloride. And this is the number of moles sodium chloride after dilution. But this also equal to the moles of sodium chloride before dilution, the concentrated solution. And we have 6 molarity of concentrated solution, so volume can be calculated. So we start with 0.12 moles of sodium chloride in the concentrated solution, and we use 6 molarity as a conversion factor, but this time we write as 6 molarity sodium chloride per liter as inverse. So this way, more sodium chloride cancel each other, and that gives you the volume in liter, and that is 0.02 liter solution. Okay, so this is the concentrated solution volume we need to make the dilution. Okay, and then you just add water to complete dilution to 0.8. Okay, so 0.02 liter portion of concentrated solution must be diluted to the final volume of 0.8. Sample problem 4.7. The beaker and the circle represents a unit volume of solution. Draw the solution after each of these changes. 1. For every 1 milliliter of solution, 1 milliliter solvent is added. And this is a dilution process. Add water, solution becomes more dilute. And the question is, how do you draw after dilution? How many solute molecules in it? Now, again, like last time, the key equation is the number of moles of the solute before and after dilution are the same. So the molarity times volume does not change before and after dilution. For this case, the given is unit volume. So unit volume is 1. So the molarity equals number of moles divided by volume. If volume is 1, then molarity equals number of moles. Okay, so in this equation we can use just the number of moles, or particles, times volume before or after dilution equals number of particles times volume before dilution. Okay, so after dilution, the volume becomes 2 moles, so 2 milliliter. From 1 milliliter becomes 2 milliliter. All right, and so in order to calculate after dilution, so this number of moles we can rearrange. So number of moles or molecules before after dilution should equals to the before dilution time divided by after dilution, the volume. Okay, and this is 1, and this becomes 2. Okay, so we can calculate the after dilution, the number of molecules in the unit volume should equals to 8 times 1 divided by 2, give you 4 particles. And so here is the drawing. Okay, now in B, 1/3 of the volume is boiled, of the solution is boiled. So when the volume becomes smaller, note that when you boil the solution, only water vaporizes, solute remains in the solution. So again, the equation is still valid. Okay, but the solution becomes more concentrated. Okay, so now what we have, we start actually with this side. Okay, and when water becomes evaporated, so if this is 1 milliliter volume, and this becomes 2/3, because 1/3 of the water is evaporated, so you only have 2/3 of milliliter of the volume exist, all right, left in the solution, and we want to calculate what is the number of molecules in the solution. So in this case, the N concentrate after evaporation becomes equals before, number of moles times volume divided by concentrated volume, and the concentrated volume becomes 2/3, and that gives you 12 particles. And so here is the drawing with 12 particles in the unit volume. Suppose we have a solution of silver nitrate, which is a colorless solution, and a solution of sodium chromate, which is a yellow solution. And if we combine them together, what will happen? Well, you will see a pink solid coming out of the solution, or precipitate coming out of the solution. And this is because the two ionic compounds react. So silver nitrate react with sodium chromate to form silver chromate, which is an insoluble solid coming out of the solution. So how do we write an equation to represent this reaction? One way to do it is the molecular equation, where all the ionic compounds are written as their formulas. So the reactants are silver nitrate, sodium chromate, and the products are silver chromate and sodium nitrate. Okay, so two molecules or formulas of silver nitrate react with one formula sodium chromate to form one formula silver chromate and two formula sodium nitrate. Now this equation is not the best way to represent this reaction, because in the solution, silver nitrate actually dissociate. You can see at the molecular level, it dissociates into nitrate ion and a silver ion. Similarly, sodium chromate dissociate into sodium ion and chromate ions. So in the solution, these soluble ionic compounds are dissociated into ions instead of these undissociated formulas. And the molecular equation only shows the reactants and the products as if they were intact, undissociated compounds. And therefore, it's not the best way. A better way is to write the ionic compounds as their dissociated ions. So silver nitrate should write as silver ion, nitrate ion. And sodium chromate should written as sodium ion, chromate ion. Okay, and the sodium nitrate, which is also a soluble ionic compound, should written as sodium ion and the nitrate ion. So if you have a 2 in front of sodium nitrate, so you should have 2 sodium ion, 2 nitrate ion. Okay, and silver chromate shouldn't written as silver ion, chromate ion. Instead, you should keep it as the formula. This is because silver chromate is not soluble in aqueous solution. So if it has a very small solubility, then you should written as a formula instead of the dissociated ions. And this kind of equation is called total ionic equation. Now, in total ionic equation, it shows all the soluble ionic substance as they actually exist in solution, where they are dissociated into ions. So it's a more accurate way to represent the reaction. Let's look at the total ionic equation in more detail. So in the reactants, we have silver ion and the chromate ion. Silver ion comes from silver nitrate. So if we look at the diagram, here is the silver ion dissociated from silver nitrate, and the chromate ion from the sodium chromate. And in the product, however, these two ions combine to form the solid. So this is a solid. So silver ion, chromate ion forms a solid silver chromate. And that's the change from the reactants to the products. Now let's look at other ions. Okay, so reactants, we also have sodium ion, nitrate ion. So sodium ion is here, coming from sodium chromate, and nitrate ion is here, that comes from silver nitrate. Now in the product, okay, sodium ion is still here, nitrate ion is still here. So if you look at the diagram, here is the nitrate, here is the sodium, ion. Now remember, when we write the formula, when we write the molecular equation, the product, one of the product is the sodium nitrate, and the sodium nitrate is highly soluble. So in the solution, it's also dissociated into sodium ion, nitrate ion in the solution. So basically, sodium ion before and after reaction, they both stays in the solution. There's no change. And nitrate ion also stays in solution before and after reaction. So they don't change before and after reaction. So these ions are called spectator ions. So in this case are nitrate and sodium. These two ions are spectator ions, and they are not involved in the actual chemical change. In this case, the actual change is silver combined with chromate to form silver chromate solid. Two ions forms a solid product. Okay, spectator ions appear unchanged on both sides of the total ionic equation. Since spectator ions are unchanged before and after reaction, they do not participate in the actual reaction, and so we can eliminate them from this total ionic equation. So in this case, nitrate before and after the same, sodium are the same, so we eliminate them. So what we have left is silver ion, chromate ion from silver chromate, and this is called net ionic equation. Net ionic equation shows only the actual chemical change. The chemical reaction shown in the last example is also called a precipitation reaction. In a precipitation reaction, two soluble ionic compounds react to give an insoluble product called a precipitate. The precipitate forms through the net removal of ions from the solution. In this case, is the silver ion and the chromate ion are removed from the solution and becomes a precipitate silver chromate. It is possible for more than one precipitate to form in such a reaction. Here shows another example of precipitation reaction. When calcium chloride and the sodium fluoride aqueous solutions are mixed together, a precipitate comes out. The reaction is between calcium chloride, sodium fluoride, and the product is calcium fluoride as a solid and the sodium chloride. In the solution, calcium chloride dissociates into calcium ion, chloride ion, and the sodium fluoride dissociates into sodium ion and fluoride ion. Now these ions, cations and anions attract each other, and when this attraction force outweighs the attraction force between this ion and the water molecules, these ions combine will become a solid. In this case, calcium ion, fluoride ion recombine and form a solid calcium fluoride. Chloride and the sodium, these two are spectator ions. They are unchanged between before and after the reaction. So the net ionic reaction is calcium fluoride forms calcium fluoride. Here are the steps to predict whether a precipitation reaction will occur. Now first, note the ions present in the reactants. For example, if we mix sodium iodide and potassium nitrate, okay, these two ionic compounds are both highly soluble. So they will ionize, okay, or dissociate into sodium ion, iodide ion, potassium ion, and nitrate ion. So these are the ions present in the reactants. So next, consider all possible cation anion combination, because only cation and anion may combine to form ionic compounds. So let's look at the cation sodium. Now sodium is a cation, so it can combine with another anion, for example, iodide or nitrate. Now if we combine with iodide, it goes back to the sodium iodide. So that doesn't go to anywhere, it's a reactant. Now if there's a possibility it combines with nitrate, forms sodium nitrate. So that's a possibility. Okay, let's look at the potassium. Potassium is a cation, it can combine with nitrate, but that's go to the reactants. Another possibility is combine with iodide. So possibility is potassium iodide. Okay, so these are the possible combinations. And the next step is to use the solubility rules to decide whether any of these ion combination is insoluble. All right, so in the next few slides, we'll show you the solubility rules. And you will see that group 1, sodium, potassium, cations, the salt are all soluble. So sodium nitrate is very soluble. Potassium iodide is very soluble. So if the reaction does occur, then you would see the product is still dissociate into ions. So sodium ion, potassium ion, iodide ion, nitrate ion, and these are the same as the reactants ions. And so these are all spectator ions, and there's no net precipitation reaction will occur. So no precipitation reaction occur. Here are the solubility rules for ionic compounds in water. Rule number 1. All common compounds of group 1 metal ion cations are highly soluble. So any anion combined with lithium, sodium, potassium, rubidium, cesium are highly soluble. Okay, so lithium sulfide are highly soluble, and let's say potassium phosphate, okay, must be highly soluble because the cation is group 1 metal. Okay, so they are all soluble, no exception. Rule number 2, all common compounds of ammonium cation are also soluble. Okay, so ammonium bromide, okay, or ammonium carbonate, okay, must be soluble because the cation is ammonia, and there's no exception. Any anion combined with these cations, they are highly soluble. Okay. Next is for anion. So any salt, okay, have anion of nitrate, acetate, or perchlorate are highly soluble. So any cation, so let's say iron nitrate, must be very soluble, okay, or calcium perchlorate, okay, must be very soluble because the anion is nitrate, is perchlorate, all right, or acetate. So these three rules, rule number 1, rule number 2, are about cations. They are all soluble. And rule number 3 is about anions. Okay, any cation with these anions are highly soluble. There's no exception. Okay, rule number 4. So 4, 5, 6. Okay, these are about anions that most of them are soluble, but there are exceptions. So now you have exceptions. So for the anions of chloride, bromide, iodide, they mostly are soluble. Exceptions are with cations silver, lead, copper, and mercury. Okay, so for example, calcium bromide. This must be soluble because all common chloride, bromide, chlorobromide are soluble unless you have silver. Silver chloride is insoluble. It's a white precipitate. And lead bromide, okay, that is an insoluble compound. Okay, so any chloride, bromide, iodide combined with these silver, lead, copper, iodide, these are exceptions. They are insoluble. Okay, next is fluoride. Fluoride is similar to chloride, bromide in that lead fluoride is also insoluble. Okay, but for fluoride there are more, and that is fluoride with group 2. For example, calcium fluoride is insoluble. Okay, and calcium strontium fluoride must be insoluble. Okay, so group 2 of metal ions with fluoride are insoluble. Okay, next is sulfate. Sulfate, the salts are almost all soluble except here, again, group 2, calcium, strontium, barium, these are group 2 metals. These salts are insoluble. And silver, lead, okay, they are insoluble. So these are exceptions. So fluoride, bromide, iodide, and the chloride, and the sulfate, these anions, mostly soluble. There are exceptions are here. Okay, you need to spend time to memorize them. All right. So far we talk about the soluble ionic compounds. Next is insoluble ionic compounds. So hydroxide mostly are insoluble. Okay, there are exceptions. What are exceptions? Of course, if it's group 1, for example, potassium hydroxide must be soluble. Why? Because you have potassium, it's group 1. That's here, the rule number 1. Group 1 metals are all soluble, even with hydroxide. Okay, and calcium, strontium, barium, hydroxide, these are soluble. Okay, these are exceptions. Otherwise, hydroxide will be insoluble. For example, iron hydroxide must be insoluble. Chromium hydroxide must be insoluble. Okay. Next, any cation with carbonate, phosphate must be insoluble except group 1 and ammonia. Okay. So this is group rule number 1. Rule number 2. Right? Rule number 1 is group 1. Rule number 2 is ammonia. They must be soluble even with carbonate, phosphate. Otherwise, they are insoluble. For example, calcium phosphate, okay, must be insoluble. All right, so all cations except group 1 and ammonia. Lastly, sulfide. So sulfide with any cation are insoluble except group 1 and ammonium, and here including group 2. Let's look at an example. Suppose we mix 2 solutions of sodium iodide and lead nitrate. Will there be a precipitation reaction occur? Well, first we need to identify all the possible ions in the solution. Now we know from rule number 1, solubility rule number 1, group 1 metal cation salts are all soluble. So sodium iodide must be highly soluble. Okay, from rule number 3, nitrate ion, all common salts are soluble. So lead nitrate must be highly soluble, and therefore both of these compounds will dissociate into ions. So in the solution, we should have sodium ion, iodide ion, lead ion, nitrate ion. So next, we are going to combine all the possible cation anions. So for sodium, okay, reactants is from or with iodide. So we need to search for another anion, which is nitrate. So it's possible to form sodium nitrate. Okay. Another one is lead. So lead will combine with iodide. So it's possible to form lead iodide. Okay. So next we are going to look at the solubility rule. Are they soluble? Well, again, this is very soluble. It's a group 1 metal and with nitrate. So it's rule number 1 and rule number 3. They are highly soluble. All right, and therefore you get ions, sodium ion and nitrate ion. Now, what about the lead iodide? Okay, well, that's rule number 4. Rule number 4 says all iodide salt are soluble except some cations including silver and lead and copper and mercury. Okay, so iodide combined with any of those are insoluble, and therefore lead iodide will be a precipitate, and therefore we predict the product will be lead iodide, and the sodium ion, nitrate ion are the spectator ions in the solution. So we can remove sodium ion from reactants product, and the nitrate ion cancel. So the net ionic reaction will be lead plus iodide forms lead iodide. And the molecular reaction will be lead iodide plus sodium nitrate. Okay, so we predict there's a precipitation reaction. And here is the diagram shows that when lead nitrate pour into sodium iodide, and you see yellow precipitate coming out of the solution, and that's the lead iodide precipitation. Now, precipitation reactions are also called double displacement reaction or metathesis reaction. So in this reaction, sodium iodide, you can consider sodium is displaced by lead to form lead iodide. And the lead nitrate, lead is displaced by sodium and becomes sodium nitrate, and therefore it's a double displacement reaction. So in this double displacement reaction, ions exchange partners and a precipitate forms, and there's an exchange of bonds between reacting species. Sample problem 4.8. Predict whether or not a reaction occurs when each of the following pairs of solutions are mixed. If a reaction does occur, write balanced molecular, total ionic, and the net ionic equations and identify the spectator ions. To answer this question, we need to first identify all the reactant ions, the cations, the anions in the solution, and write the possible cation-anion combination, and then use the solubility rule to decide if the combinations are soluble or insoluble. Write the appropriate equation for the processes. Question A. Potassium fluoride and strontium nitrate. So potassium fluoride formula is this one, strontium nitrate. So this is group 1 and this is group 2, but the anion is nitrate. So both of these, okay, group 1 metal cation and the nitrate salts are all highly soluble. So in a solution, you should have potassium cation, fluoride anion, strontium cation, nitrate anion. So the product would exchange the ions. So potassium with nitrate, fluoride with strontium. So the possible product would be potassium nitrate, strontium fluoride. So now we look at the solubility rule. Again, this is group 1 metal cation, and this is nitrate anion, so this salt should be highly soluble. Now this one is a fluoride, and we know fluoride with strontium is insoluble, and therefore this is a insoluble combination. So the reaction will have a precipitate, that's strontium fluoride. Okay, so now let's write the molecular equation. So this is the reactants. The product is potassium nitrate and strontium fluoride, and note that strontium fluoride is a solid, it's a precipitate. Others are aqueous solution. Okay, so you need to balance this equation. So next is total ionic equation. So the soluble, these are soluble, so you should dissociate into ions. And the same as this one, but not this one. Okay, this is insoluble. So here is the total ionic equation, and so you can see potassium fluoride becomes potassium ion fluoride ion, and here strontium ion nitrate ion, and the potassium nitrate, but not strontium fluoride. It's a solid. Okay, so that's the total ionic equation, and you can see potassium doesn't change, so that's a spectator ion, and strontium, not strontium, nitrate are spectator ions. So the only thing left is fluorine and strontium, give you strontium fluoride, and that would be the net ionic equation. Question B, ammonium perchlorate and sodium bromide. So here are the formula, ammonium perchlorate, sodium bromide, and these two are both highly soluble because all ammonium salts are highly soluble. Perchlorate salts are highly soluble, and sodium group 1 metal cation highly soluble. So in the solution, we should have ammonium cation and perchlorate anion, sodium cation, bromide anion, and if this reaction take place, they should exchange ions. So ammonium should combine with bromide, and the sodium with perchlorate. So here are the possible products: ammonium bromide and sodium perchlorate. Now look at the solubility rule, and this should be highly soluble because it's ammonium salt, and this should be highly soluble because it's a group 1 metal and also perchlorate, and therefore here is a possible molecular equation. So that's the possible product. And if you write total ionic equation, the reactants product are all ions dissociate. So ammonium in the reactants is a ion. In the product is also ion because both are highly soluble. Same thing is for perchlorate, sodium, and the bromide. So these are all spectator ions. Okay, so all ions are spectator ions. There's no net ionic equation, and therefore there's no reaction occur for these two mixtures. Sample problem 4.9. The following molecular views. So these views show reactant solutions for a precipitation reaction. In question A, which compound is dissolved in beaker A? So here, and the possible salts are potassium chloride, sodium sulfate, magnesium bromide, and silver sulfate. Okay, so look at the beaker A. Cation is 1 plus, anion is 2 minus, and therefore we look at the salts. The cation is 1 plus, and so this is not right because magnesium is 2 plus, and so potassium, sodium, silver are all 1 plus, and the anion is 2 minus. So this one is not right because chloride is 1 minus, and sulfate is 2 minus. So we have two possible salts: sodium sulfate, silver sulfate. Now, which one is the correct one? Well, if we look at the molecular view A, all the ions are separated, means they are dissociated. The salt must be highly soluble. According to the solubility rule, sodium sulfate should be highly soluble because it's group 1 cation salt. Now, silver sulfate is not soluble because most sulfate salts are soluble, but there are exceptions, and silver ion is one of the exceptions. Silver sulfate is insoluble, and therefore it won't dissociate into ions completely. So the answer is sodium sulfate in A. Okay, let's look at B. Which compound is dissolved in beaker B? All right, so let's look at the B. Now this time the cation is 2 plus, anion is 1 minus. Okay, 2 plus, 1 minus. Okay, so let's choose cation 2 plus. First one is not right because ammonium is 1 plus, so that's not correct. Now others are all cation 2 plus, but the anion sulfate is 2 minus, so this is not right. 2 minus. Okay, the other two are both right. Barium nitrate, calcium fluoride, and they both have cations 2 plus and anion 1 minus. Okay, now let's again look at the solubility. In the beaker, all ions are separated, and so the salt has to be soluble. And barium nitrate must be highly soluble because all nitrate ions are soluble. Okay, now calcium fluoride is insoluble, so this is not correct because fluoride, although most fluoride are soluble, the exceptions are group 2 metal cation. Calcium is one of them. Calcium fluoride is insoluble. Okay, so our choice for B is barium nitrate. Question C. Name the precipitate and the spectator ions when solutions A and B are mixed, and write balanced molecular, total ionic, and net ionic equations for any reaction. So first, from A and B, we already identified the solutions are barium nitrate, sodium sulfate solutions. Now these solutions are both highly soluble, and in the salt we have barium ion, nitrate ion, sodium ion, and sulfate ion. So the possible product would exchange ion, so barium with sulfate, so get barium sulfate, and sodium with nitrate. So the possible product would be barium sulfate, sodium nitrate. According to solubility rule, sodium salts and nitrate salts are highly soluble. Sulfate salts are mostly soluble except group 2 cations. So barium is one of them. So barium sulfate must be an insoluble solid. Okay, so that's the precipitate that would be formed. That's the barium sulfate. So let's write the molecular equation. Reactants, barium nitrate, sodium sulfate, product, sodium nitrate, barium sulfate, which is a solid here. Okay, to write the total ionic equation, the soluble salts are all dissociated into ions. So barium ion, nitrate ion, sodium ion, sulfate ion, sodium ion, nitrate ion. The only thing that is not dissociated is the insoluble solid barium sulfate. Okay, so sodium is a spectator ion, sulfate is a nitrate is a spectator ion, so two spectator ions, and then barium react with sulfate to form barium sulfate, and that will be the ionic reaction. Sample problem 4.9. If each particle represents 0.01 mole of ions, what is the maximum mass of precipitate that can form? So here is the net ionic equation. Okay, so the reactants are barium and the sulfate. And these reactants, the number of moles can be found from the beakers. For A, we can find sulfate, which has a -2 charge. So this is 1, 2, 3, 4, 5. So there are 5 sulfate particles. And since each particle is 0.01 mole, so we can calculate the number of moles of sulfate ions in the solution. Similarly, in B, we find barium. Barium is 2+, so 1, 2, 3, 4. So we can find 4 particles, and then we can find the number of moles of barium in the solution. Now here is important. If you have a reaction, and if you know more than one reactants, the number of moles, then one of them may be the limiting reactants. The other one may only react part of it. So it is important that first you need to find the limiting reactant. And to find the limiting reactant, you have to assume each of them will be all consumed, and find the product, number of product that can be made by each of them. The smaller one is the limiting reactant. Okay, so let's start with barium. So barium, we already counted 4 particles, and we calculated the number of the moles. So 4 particles, 1 particle is equivalent to 0.01 moles. So particle cancel, give you moles of barium. And then use the stoichiometry. 1 mole barium is equivalent to 1 mole barium sulfate as a conversion factor. So cancel moles of barium, give you moles of barium sulfate. All right. So if all barium ions are consumed, then we can generate 0.04 moles of the product barium sulfate. Okay. Now let's calculate the product from sulfate. So 5 particle, 1 is equivalent to 0.01, and so that gives you moles of sulfate. And according to stoichiometry, here 1 mole sulfate, 1 mole barium sulfate. Again, use a conversion factor. So cancel moles of sulfate to give you moles of barium sulfate. So if all sulfate ions are consumed, then we can make 0.05 moles of barium sulfate. And since this is smaller, that means barium is the limiting reactant, and sulfate only consume part of it. So the maximum product would be 0.01 or 0.04 moles of barium sulfate. Okay, so the question is ask you grams of the product. So we need to multiply by the molar mass of barium sulfate, which is 233.4 grams. And so the answer give you is 9.3 grams of barium sulfate. And that's the maximum product that can be produced. All right. Now, I want to mention that when you use stoichiometry, the net ionic reaction must be balanced reaction. Here shows relationships among quantities of substances for calculations involving reactions. The key is the balanced reaction equation, and this shows you the stoichiometry between all substance, reactants, products in terms of number of moles. So if given is the mass of the reactants or volume or number of entities, the first step you need to convert them into moles of the reactants. And then using the balanced reaction equation, you can calculate the moles of the product. And from the moles of product, you can calculate the grams, you can calculate the volume, entity. Okay. Similarly, if you know grams of the product, first step you need to also convert to moles of product, and then use the stoichiometry. You calculate the moles of the reactants, and then change to mass or volume or number of entities. Sample problem 4.10. Magnesium is the second most abundant metal in seawater. The first step in its industrial extraction involves the reaction of magnesium ion and calcium hydroxide to precipitate magnesium hydroxide. What mass of magnesium hydroxide is formed when 0.18 liter of 0.0155 molarity magnesium chloride react with excess calcium hydroxide? Now first, for this type of question, you need to convert the statement into a balanced reaction equation. The reactants are magnesium chloride, calcium hydroxide. So we write magnesium chloride, calcium hydroxide. React to form product is magnesium hydroxide. So magnesium hydroxide, and the other one must be calcium chloride. And you balance the reaction. Okay. So next, we want to find what is the given information? What is need to be calculated? The given is the volume and the molarity of magnesium chloride. So magnesium chloride information are given. And we want to calculate the mass of the product magnesium hydroxide. Okay, we want to calculate grams. So as we know, the stoichiometry is based on molarity, so it's based on moles. So first we need to calculate the moles of the reactants magnesium chloride using volume and molarity. Okay, we can calculate the moles, and then use this information stoichiometry. We can calculate the moles of the product magnesium hydroxide. From moles, then we can calculate the grams using molar mass. Okay, so first step is the moles of reactants, and the second step use the stoichiometry to calculate the moles of product, and third step to calculate the grams. Okay, so let's calculate moles of the reactant. So we use volume and molarity as a conversion factor. So molarity means moles per liter. All right, so 0.0155 molarity means 0.0155 moles of the magnesium chloride per liter. So the volume cancel each other, give you moles of the magnesium chloride. Second step, use stoichiometry to calculate moles of the product. So this is moles of reactants, and the stoichiometry ratio 1-to-1 ratio. So moles magnesium chloride cancel, give you moles of magnesium hydroxide. So next, we use moles of magnesium hydroxide to calculate the grams of magnesium hydroxide. Here is the moles of magnesium hydroxide multiplied by the molar mass of magnesium hydroxide, and the answer is 0.163 grams of magnesium hydroxide. Now, in the last step, we may check the answer to see if it's reasonable by rounding the numbers. The given volume is 0.18. We can approximate to 0.2, and the molarity given was 0.0155, and we can approximate to 0.02. So this calculation is simple to give you 0.004 moles of magnesium chloride, and due to the molar ratio of the stoichiometry, we approximate give you 0.04 molarity. But since we 0.18 increased to 0.2, so you would expect it should be less than this. And what we get is this number, which is approximately 0.003. And so compare these two, it's reasonable. Sample problem 4.11. Iron hydroxide used to absorb arsenic and heavy metals from contaminated soil and water is produced by reacting aqueous solution of iron chloride and sodium hydroxide. So first, we convert the statement into a reaction equation. So the reactants are iron chloride, sodium hydroxide, and one of the product is iron hydroxide. So here is the reaction equation: iron chloride, sodium hydroxide, iron hydroxide, and the second product must be sodium chloride. So balance this equation. Okay, so next let's look at A. Question A. What mass of iron hydroxide is formed when 0.155 liter of 0.25 molarity of chloride, iron chloride? So we know iron chloride, the volume, the number of molarity, okay, of iron chloride, react with volume, molarity of sodium hydroxide. So another reactant, its volume, its molarity. So we know both reactants, the volume and molarity. We want to calculate the grams. Okay, so the mass of the product. Now this is similar to the last question that we know both reactants. Okay, and we want to calculate product, and therefore we need to determine the limiting reactant. Okay, and how do we determine limiting reactants? We calculate the product from each of them, and the smaller one is the limiting reactants. And using stoichiometry, we need to first convert to moles. So using volume molarity, you need to change to moles of iron chloride, and this one change to moles of sodium hydroxide. And from stoichiometry, we can use moles of reactants to find the moles of the product. And then from moles of product, we go to the grams of the product. Okay, so let's calculate the determine limiting reactants. Let's calculate, let's erase this. All right, so here is the first one. We have volume of iron chloride, so iron chloride, the volume, and the molarity of iron chloride is 0.25 molarity, means moles of iron chloride per liter. So you cancel volume, you get moles. All right, so now we have moles of iron chloride, and then the stoichiometry between iron chloride and iron hydroxide is 1:1 ratio. So here is the conversion factor: 1 more iron chloride, 1 more iron hydroxide. So moles iron chloride cancel, give you moles of iron hydroxide. All right, so this is the moles of product that will be formed if all the iron chloride is consumed. Okay, so that will be the product. So now let's calculate the product from sodium hydroxide. So here is the volume of sodium hydroxide, and here's the molarity. So that gives you number of moles, and then you use the stoichiometry: sodium hydroxide, 3 sodium hydroxide, 1 iron hydroxide. So 3 sodium hydroxide moles sodium hydroxide, 1 more iron chloride hydroxide. So you cancel moles of sodium hydroxide, you get moles of iron hydroxide. So you divide by 3 here, and the answer is 0.0215. And so compare these two, we can see this one is smaller, okay, and therefore sodium hydroxide should be the limiting reactant. Okay, so sodium hydroxide is the limiting reactant, and the product formed will be this amount, 0.0215. That's the number of moles of iron hydroxide that will be formed. And to calculate grams, we times molar mass. Okay, so we use 0.0215 moles of iron hydroxide times molar mass of iron hydroxide, and the answer is 2.3 grams of iron hydroxide. In question B, it asks you to write a reaction table for this process. Well, as usual, we write a table like this: the balanced reaction equation, the initial amount, the change, and the final. Now for initial, we already know the molarity, okay, molarity and the volume for iron chloride, so we can calculate the number of moles, and we do the same for sodium hydroxide. We also know the molarity and the volume. So these are the calculated numbers, the moles of iron chloride, the moles of sodium hydroxide. So these are the initial number of moles. Products are all zeros. Now next, how do we decide the change? We already decided the limiting reactant is sodium hydroxide. That means sodium hydroxide all reacted, consumed in the reaction. Okay, so the change must be 0.0645, and the final must be 0 because this is the limiting reactant. It will all be consumed. So we have 0.0645. Okay, and then how do you calculate others? Well, we look at the stoichiometry. For iron chloride, ratio 1 to 3, and therefore if we know the change for sodium hydroxide, we divide by 3, and that gives you 0.0215. And same for iron hydroxide formed. For sodium chloride, it's the coefficient is same as the sodium hydroxide, so the change must also be the same, 0.0645. And then we calculate the final, and you can see in the final, sodium hydroxide all consumed, 0 left. And iron chloride, you still have some concentration, 0.0173. And these are the product we formed, all right? So that's just we calculate in the last slide.